In this tutorial, we will tackle the three-body problem. What I mean by three-body problem is where you have animation where each one of the ellipses changes its radius and they don't cross each other. They are responsive to each other's size. So as you can see, they animate and push each other away, never crossing each other's boundaries. We can do this in Cavalry with math, so everything is responsive. I think this will be a good problem to solve if you want to learn how to use math in Cavalry to create dynamic animations. I'll make sure to include the project file we'll create on the Gumroad store with all the examples where you'll be able to play with them for a small donation fee. What we need is 3 ellipse shapes with same radius on both width and height, like this, and with different colors. So I already created them, like so, and I named them as circle 0, 1, and 2, so it's easier for you to follow. It's a simple shape, as you can see, with parented text layer to it. So the math problem we need to solve is how to position each one of the ellipses dynamically, so when they change size, the other ones get pushed away so they don't overlap each other. And this can be done by calculating the distances from each one of these circles and angles and positioning them accordingly. And what we're going to do is simply follow all of these formulas and apply them to each of the circles so they are responding to each other radius or size. I won't get into details of every single formula because there are better resources for this online, but I will show you how you can use Cavalry tools to calculate each one of these values. So let's get started. First, we need a math node. I'm going to switch it to operation of add and name it side A. Duplicate it 2 more times and rename it as side B and side C. So I have side A selected. I'm just going to pan to the top and I need to find the radius of the circle 0, which is this value. Let's plug it into the first field, then find radius of the second circle, the C1, plug it into the second field of side A node, select side B, get the radius 0, which is this one over here, plug it into the first field, then finally grab the radius R2, which is this circle C2, grab it and plug it into the second field of the side B node, get rid of it, finally select side C. And repeat this again with R1, which is radius of the circle 1, which is this value, plug it into the first field, and find R2, which is this circle over here, the red one, grab the radius and plug it into the second field of side C. So essentially, we have distances between each of these circles, like so at this point. If I just pin it to the top and, for example, change the radius of the first circle, you can see the values update accordingly. Just going to undo this for now. Then let's position the first circle at x and y of 0. Position x and y at 0. Perfect. Next, we need to figure out the position of the circle 1, and the best way to do this is simply grab the circle 1, make it a child of the bigger circle, the C0. So this way, the circle 1 will inherit the position of the circle 0 and we'll be able to offset it based on the radius of circle 0 and circle 1. So the way we can do this is by simply using this A value, which is the length over here, and we can just grab it and drop it on the X position. And I need to zero out the Y value. So let's check if everything's working correctly. I'm going to turn off the red circle. I'm going to change the position of C1 and change the radius of C2. So as you can see, both circles respond without problems. So now we need to calculate the gamma angle, which we will use all the way here. So the way to do this is by creating JSMath node, and this node will allow us to create this whole calculation. So the way JSMath node works is it allows us to create fields as needed, and you can input different values here, and by using this field on top, you can create your own calculations. And you do this by recalling the index with n and the field number, as in this case 0 and 1, and for example, we can add both of them together. And we can use this result in further calculations down below over here. You should read more about the JSMath nodes on the official documentation, as well as on the HTML cheat sheet website, because we'll be using these math calculations later on over here. So I'm going to create 3 more fields. Each one of these fields will contain all the data from this part of the tutorial, and I'm going to rename them accordingly. So first, I'm going to name this one as side A to the power of 2. This one as side B to the power of 2. And the last one, side C to the power of 2 as well. And finally, simply we need side A and side B. So next I need to add a math node to the first 3 fields, like this. I'm going to parent it underneath this JSMath node. And what we have to do is grab the result of this calculation, the length between radius 0 and radius 1, which is this one, side A, and switch the operation to the power and change it to 2. So we have result of this value over here, A to the power of 2. Do the same thing for the second node, for the side B to the power of 2. We need to grab side B, drop it in the first field, and change it to the power of 2. Same thing with the last one, side C, grab the side C layer node, drop it on the first field, and change it to the power of 2. So essentially what we did is just calculated the length squared for every single side of the triangle. I mean this triangle over here between these 3 ellipses. And next we need to grab just plain side A calculation, drop it in this field, side A, which will represent this value over here, and then grab it side B and drop it on the final indice over here, which will represent this digit over here. So how do we write this formula over here? It's pretty simple. We have to open the bracket and then input n0, which is side A squared, add n1, which is side B squared, and subtract n2, which is side C squared. And that gives us this value. Then we need to divide the whole thing by 2 times side A, which is n3, and then again times n4, which is side B. And that gives us this value, which is the gamma angle over here. I'm going to rename this math node to angle gamma, so we know which one's which. Next, we need to clamp this gamma angle to -1 to 1, so the whole thing is a little bit more stable. Essentially, we are normalizing these values. So we can do this with JSMath node. We need to grab the result of this calculation before, drop it on the first field, and I'm going to rename it as angle gamma, so I know which one's which. Just going to parent like this. And now we need to write this formula. And as I mentioned before, we are going to use math min and math max over here. And we simply need to write math.max -1, math.min, open brackets 1, and then recall the cos angle of gamma and 0. And that gives us this value over here. I'm going to rename this math node to clamp angle gamma to -1 to 1, so I know what is going on. Okay, one more step. So we need another JSMath node. Then we need to grab the previous calculation, drop it on the N0 field. I'm going to rename it as clamp gamma angle. Okay, so what we need to do is we need to write this formula, which simply looks like this: math.a cos, and then in the brackets we just need to put N0. I'm going to rename this JSMath node as inverse cos gamma, put it on top, and just parent everything underneath it, so the whole thing is a bit better organized. Finally, we are coming to an end of our calculations, and now we are going to tackle the position of the final third ellipse. So what we need to do is, again, we need to parent it to the C0, to the main sphere, because this is the sphere that will drive all the calculations, and we need 2 JSMath nodes. We will need 2 fields, one for side B and one for this calculation over here, the inverse cosine function. So let's call this side B, and this one will be inverse cos gamma. And as before, we are going to use side B node to populate this value over here, and finally inverse cos gamma result and drop it into this field over here. So this node will be called position X. I'm going to duplicate it and call it position Y. So let's select position X first, and I'm going to simply recall N0, which is side B, multiply it by math.cos value of N1, which will give us this value. Then let's select position Y and do the same thing. Recall index of N0, multiply it by math.sin, and in the brackets N1, which will give us this value. Going to parent these 2 nodes to C2, the red ellipse over here, and we simply have to take position X, drop it on position X over here, and finally, if everything goes well, grab position Y, drop it here, and as you can see, this sphere is perfectly positioned in a way that it touches C1 and C0 without crossing the boundaries. So let's do a final check and resize each one of these spheres to see if everything is working correctly. So to clean this up a little bit, I'm going to rename these 3 math nodes. These guys over here, the side A squared, B squared, and C squared, to simply side A squared, B squared, and C squared, so it's a little bit easier to read. And simply, I can put all of these guys into a group, so everything is easier to read and follow. And if you did everything correctly, you can use, for example, noise to easily animate every single one of these ellipses like this. So they will animate and push each other and so on according to the settings on your noise modifier. Like this. I hope this was useful in understanding how you can use math nodes and JSMath nodes to create complex animations using math, and how you can translate math equations into nodes. I'll make sure to upload project file to Gumroad. We'll be able to take apart all the examples I put together. Thanks for watching.